Right, now, as you may remember, we have started a new chapter about sampling, and we started by saying that the critical issue about sampling is with respect to the sampling frequency and the corresponding signal's highest frequency, maximum frequency. So if well, of course, we do the sampling by multiplying our continuous time signal, something like the one at the top, with an impulse train. We just multiply them to produce something like this. Of course, it's an intermediate step in discretization, discrete time conversion, which is also known as sampling. And the phenomenon that goes on in the Fourier domain is like this. If the signal's Fourier transform is band limited between -w and w, something like this, then automatically the Fourier transform of the impulse train is another impulse train, which is given like this. And the impulse magnitudes are 2 pi over capital T's, whereas the period of the impulses along the frequency axis, along the axis of omega, is given as 2 pi over capital T, which is also known as the sampling frequency. Okay, so 2 pi over capital T is the sampling frequency. The impulses are separated by sampling frequency. And since we multiply in the time domain, we need to convolve the two shapes in the frequency domain, and the convolution will result with replicas of the band pass signal, low pass signal's shape to band passes around the frequency of the sampling. So this is the situation, and for these shapes not to overlap, we must have the sampling frequency omega s to be greater than twice the maximum frequency in our signal. So omega s must be greater than 2w, as given here, which is also known as the famous Nyquist criterion. If that doesn't happen, what we observe will be a phenomenon called aliasing. They overlap and we cannot resolve, because the way to resolve is to low pass filter the sampled signal's baseband version, to extract it and get rid of the others, which corresponds to the same shape as the original Fourier transform. So typically that's what we have. Now, I said that the impulses, the continuous time impulses, correspond to the intermediate discrete time signal. It's not a discrete time signal, it is still a continuous time signal consisting of some continuous time impulses like this. Okay, it's still not discrete time, because we have continuous time impulses, and the separation is like this. All right, on the t-axis. Now we have to somehow, so let's call this thing something like this, xp of t. It is impulse train multiplied version. It's an intermediate step in discretization or sampling. We have to somehow convert this to a signal along the n-axis, and n, as you see, is an integer. And then we will have not xp of t, not a function of t, but a function of n. X of n is what we're going to have. So the thing that we need to have is something like this then. It's not the same impulses that I draw, as you see. These impulses are discrete time impulses with some filled circles on top of them. And the indices are not 0, capital T, or anything. There is no time that we can think of. There are only indices. So this is 0, this is 1, this is 2. 3, 4, minus 1, minus 2. So the situation is like this. From here to here, we need an extra conversion. And those conversions are nothing but measurements. Typically, the system analog to digital conversion system just makes a measurement here and assigns it to the index, and then makes another measurement here, another measurement here. They just the system just evaluates the magnitudes of those impulses and assigns them into an array. Now this array is a discrete time sequence now. We can safely say it. But how about the relation between their Fourier transforms now? In other words, we have seen the relation between xp of t towards x of n. So what happens to xp of j omega, which was here? This one, as I previously said, y of j omega is essentially xp of j omega. Okay, that's the intermediate signals Fourier transform I'm telling you, with the triangular replicas, for instance. So how can we relate that to the Fourier transform of the discrete time signal, truly discrete time, which is x of e to the j omega? What's the relation between them? And the relation between them is quite simple. We have to first observe what's going on between xp of t and x of n, the top shape and the below shape. What's the relation between them? If you consider the time axis, in both cases, as the time axis, what is the fundamental difference between them? The fundamental difference is the time separation of t reduced to a time separation of 1 to become integer indices. So time is divided by capital T. Here we can say that the new time, let's call it t prime, became the previous time over capital T, sort of thing. So that every separation of capital T became a separation of 1, 2, 3, etc. So we may expect that the frequency, on the contrary, the frequency must be multiplied by capital T. And does that really happen? Let's see the shape of xp of j omega again. So I'm drawing xp of j omega on the omega axis, on the frequency axis. It's just an illustration. So this is 2 pi over capital T. This is 2 times 2 pi over capital T, where 2 pi over capital T is the sampling frequency omega s. This is 0. This is minus 2 pi over capital T. Now let's multiply the horizontal scale of omega by capital T. Then what are we going to get? This is again, what is that? This is again the frequency axis I'm saying. The shape will be the same. It is just a squeezed or expanded version of the top shape. So it's going to be the same shape. Let's narrow it down a little bit just to make or to illustrate some difference between the two shapes. Now here, what will be the center? Remember that all the frequency axes are multiplied by capital T. So what is our new center for the second triangle? It was previously 2 pi over capital T, now it is 2 pi. And then this one will be 4 pi. This one will be minus 2 pi. And I'm saying that this corresponds to x of e to the j omega. And this new representation is totally compatible with our intuition, saying that the discrete time Fourier transform of a discrete time signal must be 2 pi periodic. Okay? I have repeated this like 1,000,000 times perhaps. this must be 2 pi periodic. Now is this 2 pi periodic? Yes. So we are safe. And this is indeed the thing that you need to do. So the path between the original continuous time Fourier transform and the discrete time Fourier transform of the sampled version is as follows. You start with an original triangle which consists of sorry, only the single triangle in the center. Then we just repeat it with in the frequency axis. We just repeat it with a period of omega s, which is the sampling frequency. That is 2 pi over capital T, and the corresponding discrete time Fourier transform of the sampled signal, the real sampled signal, is nothing but a scale on the frequency axis, which doesn't change the shape actually. It's just squeezing depending on the value of capital T. And we make it not 2 pi over T periodic, we make it 2 pi periodic only. Every 2 pi over capital T is reflected to a 2 pi. So that's it. And the digital to analog conversion step is also quite simple. It's just the opposite of it. We start with these discrete time samples. And at the positions of these discrete time samples, not separated by one, but separated with the sampling periods, we insert impulses, continuous time impulses. We must somehow do this. Of course, there is no practical way of inserting a true impulse from a circuit. What the circuit usually does is insertion of a pulse, a narrow, tall pulse. And those pulses are separated by not integer indices, but by the sampling period. So the knowledge of sampling period or the knowledge of sampling frequency, they correspond to inverses of each other simply, is necessary. If you forget somehow the sampling frequency or the sampling period after getting this, suppose you have a discrete time signal only, and you don't know from which signal it came from. Okay? So you just forgot, for example, the sampling frequency. There is no way that you can revert the operation. Without the knowledge of the sampling frequency or the sampling period, you cannot make a digital to analog conversion, because you cannot separate these impulses, which were just separated by one in discrete time, just the index in the array, without the knowledge of this zero capital T separation in the original time axis, you cannot revert the operation. But if you know it, you just insert the impulse like that and apply a low pass filter. That's it. And the cutoff frequency of the low pass filter is also deterministic. It is sampling frequency omega s over 2. It is right in between 0 and omega s, and the cutoff frequency of the low pass filter must be there. And in the frequency axis, the situation is quite simply like this. You start with the Fourier transform of your discrete time signal, which is 2 pi periodic, and then you expand or multiply the frequency axis by 1 over capital T, or divide everything by capital T. And as you see, you need to know this capital T. Without knowing that, you cannot go from here to here. Once you know it, you just scale the frequency axis by 1 over capital T, and you get those new triangular shapes, repetitions. Then you just apply a low pass filter whose cutoff frequency, as you see, is just the half of this sampling frequency omega s. This is just the half of it, omega s over 2 is the cutoff frequency. So that is digital to analog conversion phenomenon illustrated along the frequency axis. This thing the low-pass filtering with a cutoff frequency of omega s over 2 has an interesting property. In fact, yesterday, after the class was finished, one of the students came and asked me what kind of an interpolation does it correspond to if we have these impulses xp of t. What is the interpolation? I said that the low-pass filtering is an interpolation. And it is indeed an interpolation. It is just tracing the dashed envelope that I have drawn. So what kind of an interpolation does that mean? He said we know interpolations such as zero-order Hall interpolations, just rectangular shapes. We know linear interpolation, first-order Hall, which is interpolating the peaks of these impulses with a line. But this interpolation, corresponding to this low-pass filtering, is another way of thinking of the interpolation. Let me illustrate what I mean. That thing is known as the sinc interpolation. That is the name, and it happens like this. Suppose that the impulses, well, these are too near to each other. Let's make them a little bit separated. The impulses are like this. If we have these impulses, what do we mean by a sinc interpolation, or what kind of an interpolation is it in the time axis? In the frequency axis, the situation is simple. It is just low-pass filter. And look at the shape. What shape is that? The low-pass filter shape? It's a rectangle. No. In the frequency domain, the low-pass filter is a rectangle. Therefore, in time domain, the corresponding impulse response of that filter is a sinc. Do you agree with that? Alright, then we need, since we are multiplying in time domain, we need to convolve these impulses with the sinc, the impulse response. So when you convolve with impulses, what was the thing that you did? You're just replicating the sinc shape. The impulse response is repeated at the first impulse, at the second, third, etc. They are all just repeated and scaled with the impulse. And the situation that you get when you choose the cutoff frequency to be precisely equal to omega s over 2, which is pi over capital T, in other words, then the sinc that you draw will become like this. Okay. This is the sinc that you will draw when you convolve it with that particular impulse. When you convolve the sinc with the impulse at the origin, then it will be having a peak like this. When you convolve it with the one at capital T, it will be like this, the sinc shape. When you convolve it with this one here, it will be like this. And when you convolve it with this one, it will be like that. Now, can you feel what kind of an interpolation you would get when you just add up all these things, when you combine these things? What is the thing that you will get? It is just the trace, the original envelope that you get when you add up all these sinc shapes. So let's draw it with a red, for instance. So the combination of these sinks will follow the envelope. Interesting, isn't it? Another interesting issue is that the zero crossings of these sink shapes happen at the next impulse position. For instance, this is just making a zero crossing at this particular point, which was the next impulse. Therefore, the value at this point, at this particular point, here for instance, marked with a red, the value at that particular point is not related with the other sinks, because the other sinks are all making a zero crossing there. So it's always zero from all the rest of the sinks, but from itself, the value is this. That's why at that particular point of the summation, we have this value, which is the same as the value of the magnitude of the impulse. That is how a sink interpolation is made. And as you see, it's not a linear interpolation. It's not a zero order mode. It is only known with this particular name called sink interpolation, which is all quite fascinating. And this sink interpolation is due to the famous, you must have heard of him, Shannon. Claude Shannon, who just formulated the information theory, who also formulated the way to sample things. And this sink interpolation gives us precisely the envelope. Now, with the linear interpolation, 2 points is enough. With the sink interpolation, only 1 point is enough. But look at the sink shape. The sink shape never ends. We know it, right? It goes to infinity at both sides. Although it decays to a very small energy, nevertheless, technically we can say that it is still non-zero at infinity. So the tails of all of these things will go to infinity, which says that if you have a band-limited signal, these must be band-limited signals. The band-limited signals must be infinite extent. You cannot have a band-limited signal which starts at a point and ends at another point. If it starts and ends, you are doomed. It can't be a band-limited signal. It can't have a Fourier transform like this, because this is band-limited Fourier transform. Every band-limited signal must be infinite extent. So technically, if you have a finite duration of a signal, starting of the recording and ending the recording of the speech or an audio, for example, when you want to digitize it, technically you are losing something because it is not band-limited. You must apply some filters to suppress the high frequencies, which is okay, sort of safe, but things are never as ideal as these ones. This is extremely an ideal way of thinking of the sampling phenomenon, and it never happens this much ideal. There are too many idealities here. The first ideality is the incorporation of impulses which never exist. We don't have impulses, they are not physical. So impulses are not there. The second ideality is a band-limited signal. A band-limited signal must be infinite extent, and we never have an infinite extent sequence. We usually start recording and end the recording. Therefore, our signals are never band-limited, unfortunately. That is the second imperfection. The third imperfection is about the application of the low-pass filter, which is an ideal low-pass filter, which produces ideal sinks, like this, because it's a rectangle. Now, an ideal low-pass filter doesn't exist in the universe. Okay? It requires infinite number of condensers, capacitors, or inductors and things like that. So you cannot have it either. Your low-pass filters are never ideal. They never produce. a spectral response of this rectangular shape at the top. This is also impossible, which is the third imperfection. So as engineers, we just need to converge to here as much as possible. We must have our pulses as narrow as possible. We must have our low-pass filters as high quality as possible, but never ideal. Okay? So that's what we're going to do as engineers. But nevertheless, this is at least the theoretical limit of sampling we can think of. And probably that's why I'm not a very keen person about the sampling business, but I believe that if 44.2 kilohertz is applied for sampling of audio, the reason that it wasn't selected 40 kilohertz, exactly 40 kilohertz, is probably due to the imperfection of the low-pass filters. That's why we need not 40 kilohertz, but 44.2. Some tolerance is necessary to be more practical. Okay? So this is the idea about sampling and the inverse operation. Now, another question was asked from that particular student in the during the break or after the course yesterday. He asked me that if we want to digitize something, if we want to capture things in computers, the computers have some finite number of bits to represent every value in an array. It can be a float array, it can be a double precision array, it can be an integer or a byte array. So 8 bits, 16 bits, 32 bits, 64 bits representations are there. But the values that we have here, we never consider how many bits are necessary to represent them, he said. And I have to agree with that, but it's not an issue of signal design systems now. That level assignment with some finite number of bits is called quantization. You have to quantize the levels too. The level is pi over capital T. Let's say capital T is 2, so pi over 2 is the value. Pi is an irrational number. You can never represent a pi in a computer. You must just assign some number of bits, which automatically describes the number of levels that you use. For example, if it is 8 bits representation, how many levels do you have to represent? 2 to the 8, 256 it means. So you have only 256 distinct levels, which is not a fine quantization. With more number of bits, you have better quantization. So that representation in computer is called quantization, and we're not going to cover it. It's a different story, but it exists, and it is a part of signal processing too. Quantization is an important signal processing issue. Together with, if you have sampling plus quantization, all of it, you can say that that process is called digitization or analog to digital conversion. It requires everything, both sampling and quantization. But here, if you remember the topic, it is only sampling. It's not digitization. That's why we're not covering quantization as a side note to you. Now, this sampling is, of course, the critical step in digitization, and there is one very important reason to use sampling, that is computer processing of continuous time signals, or discrete time processing of continuous time signals. What do I mean by that? Let me write it as a subtopic. Discrete time processing of continuous time signals. Now, in the old days, people were using mechanical systems to process continuous time inputs. Then, after the evolution of electricity and electronics, basically, people started using circuits to make controllers which takes some measurements in terms of voltages or currents, and with respect to that, it is the system is processing, which is the circuit. The circuit is processing and producing some other voltages or currents as the output, and the system just uses those outputs to control something or to make some observations, whatever. But it was the second generation, let's say. Now the third generation is, of course, computer controlling of continuous time inputs. The inputs are still in terms of voltages or currents. For example, from a microphone, when you speak, it induces mechanical vibration, and those mechanical vibrations are translated into voltage variations. Okay? But those voltage variations go into a computer. Now what's going on over there? We use the computer to control, to process this continuous time signal, and we want our computer to produce another continuous time signal. For example, audio from the speaker after the process. So the third generation, the new generation of doing things is as follows. We have the continuous time signal. I'm going to call it XC of t. And here I have the sampling. The sampling itself consists of several things. We are going to expand it again. We have already done, but not in this figure. And after this sampling, we make a discrete time process. Let's assume that that process is a linear process with a frequency response h of e to the j omega, or an impulse response h of n. And as I repeat, why are we doing this? Because that discrete time process, it can be done using the computers, which are quite powerful and very flexible. You can do many things using a computer, linear and nonlinear, that you cannot do, or you can do very difficultly using circuits. It is even more difficult to use mechanical systems, and believe it or not, it's even more difficult to use chemical systems and processes. And that's why all of the engineers which require a process must cover the Signals and Systems course, including chemical engineers, mechanical engineers, electrical engineers, and computer engineers as well. Unfortunately, nowadays, only electrical engineers and computer engineers a little bit are interested in the evolution of this mathematical topic. The other engineering disciplines have abandoned the mathematical flavor of how to process, and I feel sorry for them, because it means that they don't really know the mathematical background of their processes, which is a pity, and you must feel lucky about knowing how to process these things mathematically. So if you now go and become another engineer in another department, you still know what physically or mathematically your process corresponds to. Those guys probably don't know anymore. Okay? That's a pity for them. Now this is the discrete time process, but we need to use the computer there because it's more powerful again. And then we have the digital to analog conversion, which is the inverse operation of the sampling. I didn't show you how to do it technically, but it's, as we know, distinction or separation of the impulses with capital T, and then apply a sinc interpolation, which is low pass filtering. So that is digital to analog conversion, and the output is, let's call YC of T. Now from this XC of T to YC of T, we have a system in between. It consists of several steps, but the whole thing by itself corresponds to a system. And that system is still a linear system with a frequency response h of j omega. Okay. As a matter of fact, this is the system, the desired system that we want to design, or we want to achieve. We want this h of j omega. We know how it should behave. Now, if you know this h of j omega, in the computer, what must you do? How are we going to design h of e to the j omega of this computer? So that effectively the overall scheme corresponds to h of j omega. That is the topic. Discrete time processing of continuous time signals. How are we processed in discrete time? So that the continuous time effect will be h of j omega. I'm going to describe it using one example. And that one example is this system. Xc of t goes into a system which takes the derivative of the signal and produces yc of t. Differentiator, derivative system. So, in the computer, what kind of a thing do you need to do so that the overall effect corresponds to a derivative operation? Now, this operation, if you want to apply this operation with a computer, you must have, of course, the assumption that this xc of t must be band limited. If it is not band limited, there is no way to sample it, first of all. So you cannot do that. That assumption must be necessary. Okay? It is band limited. So xc of t has no frequency content greater than plus w and less than minus w. It is band limited. If it is band limited, now we can think of a way to process it. This system has an h of j omega is equal to what? What is the frequency response of this? Yes. No, it's j omega. H of j omega is equal to j omega. Because it multiplies the Fourier transform by j omega. So the frequency response is j omega. Can you plot j omega? Let's try to figure out what it looks like. It's complex number. It's an imaginary number, in fact. It's purely imaginary. So instead of h of j omega, let's try to draw, for example, magnitude of h of j omega, which is magnitude of j omega, which is the magnitude of omega. Alright? So the magnitude that we are going to plot is something like this, extending to both sides, like this. Are you happy with this? This is the shape of the magnitude of h of j omega. I'm drawing this because I cannot draw j omega. Okay, that's why I'm drawing it like this. Now assume that our signal is band limited between minus w and plus w. So my signal, the original signal Fourier transform is like this, which is the magnitude of x of xc of j omega. Okay? Clearly, we need to multiply xc of j omega by h of j omega, so that in the Fourier transform domain it corresponds to the multiplication with j omega corresponds to a derivative in time domain. So the implementation will be the multiplication of the black shape and the red shape. Of course, I'm drawing only in terms of the magnitude. They are in fact multiplied everywhere, not only in the magnitude, but all the complex values are multiplied. What I'm trying to indicate here is that, do we care with the rest of this curve that goes up here or here when they go beyond the value of w and minus w? When they go beyond there, do we care how the system behaves there? It's none of our business, right? The tails here and here extending to infinity, those tail behaviors are none of our business because our signal is not related with there. Our signal has no frequency content over there. So we are not interested in those tails. The only thing that matters to us in terms of this particular process for this signal is the behavior of, or the shape of h of j omega only from minus w to w. Do we agree with that? Because the others are multiplied by zeros. They could be anything. Do you agree with that? So that's where the sampling issue comes into the picture. Since we don't care about the rest, let's sample our xc of t, and the sampled signal will be xc of xp of j omega. This is the sampled by multiplying with an impulse train, and it will be the repetition of this shape with the sampling frequency. So we are just repeating what's going on. Okay, something like this. This is xp of j omega. I have repeated my signal shape, and the corresponding capital X of e to the j omega, which is the true discrete time Fourier transform of our signal, discrete time signal. It's the same shape, with the only difference that now this point is not omega c anymore, but it is 2 pi. Alright? Now I am going to implement the magnitude of h of e to the j omega, which is the discrete time system. The discrete time system is the program, my algorithm running in my computer. And it has an impulse response and the corresponding Fourier transform of that impulse response, which is the frequency response. And this is it. This is the frequency response. I'm drawing in magnitude, and I'm drawing it like this. Minus pi, minus 2 pi. So from minus pi to pi, which covers everything from here to here. So it covers all the frequency content of my Fourier transform, like that. Okay, and then the rest, I don't care, and therefore it can be like this. In fact, it must be 2 pi periodic. So the rest goes on like this. This is h of e to the j omega on the discrete time frequency axis, omega. So when I multiply this one and this one, as you see in the central portion of this, it is this shape that I apply to the signal, and the application of that shape to that signal corresponds to a derivative operation. We have seen it from here. So that shape, that is the shape that I have to get, but not for all frequencies, only within our band. And within our band, from minus w to w, I have that shape. And since my sampling frequency is greater than 2 times w, in discrete time frequency, this is the situation that I have. So the application of the below shape to the top shape, when I multiply that, it is really the multiplication of the top shape with this red frequency response. And that frequency response means derivative, differentiation. So, in short, the program or the system in my computer is this one, the last shape. That's it. After that application, what you need to do is you must take the output thing like this. So you have sampling, and then you have this h of e to the j omega from the computer, this one, and then you just do digital to analog conversion again and obtain the output. And I am saying that the whole system here corresponds to h of j omega is equal to j omega, which is a differentiator. That's how you do discrete time processing of continuous time signals. Now, if I give you another h of j omega shape, this one, if I give you another system, what are you going to do? For h of j omega equals a differentiator, this was the shape. If I give you another shape, any shape, how are you going to process using the computer? Well, what you need to do is you have to take that any shape, but take it only in the center, within the frequency of interest, because my input is band limited. I will only consider that band, the central shape of that complicated h of j omega, and repeat it, and then make it, the repetitions are originally omega s periodic. Make those repetitions not omega s but 2 pi periodic, which will automatically correspond to a discrete time system. Apply that discrete time system using your computer in the center, and then that's it. The digital to analog conversion, the rest of the system, means from here to here, the whole process corresponds to that complicated shaped continuous time system. Is that clear? Do you understand how to do it? Because, of course, I'm promising that somehow in the examination you will encounter this kind of equation. I will give you an h of j omega. I will tell you that my input signal is band limited between minus w and w. W, I will tell you what it is. Something kilohertz, for example, some particular value. And I will ask you to develop a method to apply it with a computer. And you will just repeat the central portion of that system response. Repeat it. Make it then 2 pi periodic by scaling the repetitions. And that will correspond to h of e to the j omega, you will say. You will draw me this. And that is full credits, 10 points. If you draw this, the computer program must implement this discrete time signal with this frequency response. If you give me that answer, then you get 10 points. Okay, that's how you do it. You have to draw this shape for any system. Okay. All right, now we can give some break. Yeah. Okay, let's give a 15 minutes break. After that, we will continue. I'm just unable to